All right. In this video, I'm going to cover section 15.9, and I'm going to spend 2 videos on this section. So this is the first one of them. And this section is about the change of variables in multiple integral. And multiple integral means double integral and triple integral. Essentially, what we're going to do is basically use substitution for double integrals and triple integrals. So this is basically use substitution. Use sub for double integral and triple integral. But I'm going to mainly work on double integral, and I'm going to spend a little bit of time on triple integral at the end. So essentially just use substitution for double integrals. And then let's remember use substitution. Wait. Let's remember use substitution. Use substitution. So how does that work? Well, it works like this. A, B. Suppose you have some integral you want to integrate. But typically, if integrand is some complicated expression, what you do is u is equal to some expression of x. But of course, by solving for x, you could do like x is equal to some function of u. That's what use substitution was. And then in this integral is written as g of u. And the du, but what's du? Well, from here, you could say that dx is g prime u du. So that's g prime of u du. And then accordingly, you have to change the limits from a to b to a prime b prime. So usually you get different limits if you change the variable. Okay, and then this was what the use substitution was. Let me erase this. And then the point is that dx is not going to be just du, but we need something extra in front. And then this is some kind of fudge factor. Fudge factor is some kind of factor that compensates a certain discrepancy. In this case, the fudge factor compensates the discrepancy between dx and du. And it just happens that that's the derivative of g in this case. So that's what the use substitution was. And then now, what we're going to do in this section is to generalize this to double integrals and later to the triple integrals. But in some sense, we have already seen an example for it. That's basically the polar coordinates. So let's remember. Let's record polar coordinates. Suppose you have some double integral dx dy over some region R. And then by using polar coordinates, so x is equal to r cosine theta, and y is equal to r sine theta. By using polar coordinates, this double integral is rewritten as double integral over more space. Some other region S of f of r cosine theta and r sine theta. And then the point was that dx is not going to be just dr d theta, but it's r times dr d theta. And in this case, this r compensates the discrepancy between dx dy and dr d theta. So this little r here is the fudge factor in this case. Fudge factor. Okay, then the idea is we generalize this. This to this. Suppose you have some double integral and then by using the change of variables, namely we express x in terms of some other variables u and v. So let me write this way. This notation means x is a function of u and v, and y is also a function of u and v, another function of u and v. And then this becomes a f of x, but x is going to be a function of u and v, and y function of u and v, and y is a function of u and v. So this entire expression is a function of u and v, and then we need some Fudge factor, and that Fudge factor is the absolute value of symbol like this. I'll explain this. And the du dv. So that's the Fudge factor for the change of variable in general. And then of course we get the different s. So here, so this is the Fudge factor. But what is that? So first of all, those are just absolute values. Okay, here, this is absolute value. Absolute value. But what's this? This fraction is by definition. But this is not really a fraction. This is a symbol. This is a notation. This whole symbol is partial x, partial u, partial x, partial v, and then partial y, partial u, and the partial y, partial v. And then take the determinant, remember? So this is the determinant. So you just multiply diagonally. Partial u times partial y, partial v minus partial x, partial v times partial y, partial u, partial u. And then this is called the Jacobian of the transformation, or Jacobian of the change of variables. This thing, namely this thing, is called the Jacobian. Jacobian. Of the transformation. Or the change of variable. If you make this change of variable. So for example, indeed, if our change of variable is the polar coordinates, x is equal to r cosine theta, y is equal to r sine theta. So instead of u and v, we have r theta, but it doesn't matter. And then from those, the Jacobian is in this case r theta. And once again, this is not really a fraction of anything. It's just a symbol to denote the Jacobian. So this is the determinant of partial x, partial r, partial x, partial u, partial theta, partial y, partial r, and partial y, partial theta. And if you work this out, you differentiate with r, cosine theta. And you differentiate with theta, you get negative r sine theta. And you differentiate with r, you get sine theta. And if you differentiate with theta, you get r cosine theta. And if you multiply diagonally and subtract one from the other, what you get is r cosine squared theta minus r sine theta times sine theta. So that's sine squared theta. And then this is equal to r. So therefore, dx dy, according to this rule, dx dy becomes absolute value of the Jacobian times du dv, but in this case dr d theta. So here dx dy is absolute value. Okay, this bar is for the absolute value, and this bar is for the determinant. So those have two different meanings. But anyhow, r theta, and that is dr d theta, and that is the absolute value of r dr d theta. But r is always non-negative, so absolute value is just r, and it becomes this. And this is the formula for the polar coordinates. Okay. So therefore, after all, this formula is just a special case of more general formula for this. Dx dy is equal to this. Okay, then using this, let's just work out one example. Yes. Right. Here's an example. Evaluate double integral dA, where R is the region like this. Minus or minus, this is 2. Okay, so here's the answer. So we need U substitution. Actually, it's not really U substitution, more like UV substitution, because you need two variables. And for this case, we let U is equal to X plus Y, and V is equal to X minus Y. And for this type of problem, this is always given in a problem, by the way. For homework exams, it usually says use this substitution. So in this case, we use U is equal to X plus Y and V is equal to X minus Y. And then from this, but to use this formula for the Jacobian, you have to solve X and Y for U and V. So by solving this for X and Y, you get X is equal to 1/2 U plus V, and Y is equal to 1/2 U minus V. So this is your exercise. Let's solve for. So solve for. And Y. Okay, and then the Jacobian is, by definition, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. And then this is equal to, well, you differentiate x with u, you get 1/2. And if you differentiate x with v, you also get 1/2. And now you differentiate y with u, you get 1/2. And the y with v, you get negative 1/2. And then this is equal to, now if you multiply diagonally, you get 1/4 minus 1/4. That's negative 1/2. Okay, so therefore, the given double integral over the region here is written as dA is written as e to the power of u over v times absolute value of the Jacobian and du dv. And that is equal to, so you take the absolute value, so negative sign goes away, e to the power of uv du dv over what? Over some other region, S. Remember, when you do U substitution, if you introduce another variable, the limits of integral change. And similarly here, you get different regions of integration once you do the substitution. But how are they related? So that's another difficult part for this type of problem. So where are this S are related as follows. First of all, let me just copy R. R was like this. Okay, and then here, this is just a line with the slope 1, intercept with negative 1. And then here, y is x minus 2. And then this shaded region is our region R. Then now, we make this substitution. X is equal to this, no, x is equal to 1/2 u plus v, and y is 1/2 u minus v. So x is u minus v. Then how is this going to be changed to some other region on the UV plane? Well, the way to do it is basically to check the boundaries, so to speak. Namely, there are 4 boundaries, here, 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 here. So what we're gonna do is basically to check boundaries. So basically we have here trapezoid like this, right? And then what we need is to determine how those 4 boundaries of the trapezoid changes in terms of u and v. The first one is this one. Let's just look at this one. Y is equal to x minus 1. Okay, what is this in terms of u and v? Well, we know that x is this and y is this. So therefore, u minus v is equal to u plus v minus 1. And if you simplify this, you will see that this is equal to v is equal to 1. So that means on UV plane, this is just v is equal to 1. So here, on the UV plane, we have v is equal to 1, v is equal to 1 is maybe some line like this. So this is v is equal to 1. All right, then now, x is equal to 0. What's x is equal to 0? That is 1/2 u plus v is equal to 0. And then this gives you v is equal to minus u. V is equal to minus u is a line going through the origin with the slope 1. This is v is equal to negative u. Okay, so that means, let me just say, this portion gets mapped to here, and then the vertical line here, I'm sorry, x is equal to, x is equal to 0, so that means the y-axis gets mapped to here. All right. Then now, the next one is y is equal to x minus 2. So here. This line is y is equal to x minus 2. That is 1/2 u minus v is equal to 1/2 u plus v minus 2. And if you simplify this, you will see that this gives you v is equal to 2. So v is equal to 2 is something like this. And then finally, here, that's y is equal to 0. Y is equal to 0 is 1/2. And that is equal to v is equal to u. V is equal to u is the line going through this way. And then look at the region bounded by those 4 lines. Then we get this trapezoid. This is the this trapezoid, or the thing inside this trapezoid, is the new region of integration S. And this S is the S we're going to integrate over. All right. So, therefore, the upshot is the given integral is written as 1/2 double integral e to the power of u over v du dv over S, where S is this. And let me copy it here. It's another trapezoid looking like this. Oops. And then this line here is v is equal to u, and here v is equal to negative u, and then v is equal to 2, and v is equal to 1. All right, so you double integrate this. So this is just a double integral, and by the way, this is of course a negative 2, negative 1, 1, and 2, and this is 1, 2. Then now, so this is just a double integral. So you pick up one of the variables, and you fix the variable and integrate with the other. And in this case, better to do this way. You fix v. Now for each fixed v, your u value varies from this side to the other side. So for each fixed each fixed v, u is from what? This is u is equal to negative v. And this is u is u, so it's u is v. So u is from negative v to v. And then dv. And the v is from 1 to 2. Oops. So it's from 1 to 2. Okay, so all I have to do is just work this out. And then here, 1, 2. And for this integral, we integrate with u. So we have 1 over v here, but that's treated as a variable. So if you integrate this with u, you get v e to the power of u over v. Strictly speaking, to compute this antiderivative, you have to use u substitution. But to convince yourself with your exercise. And indeed, if you partially differentiate this with u, you get this. V, and this is 1/2. 1, 2, v. And if you plug in, you get v over v minus v e to the power of negative v over v and dv. But v over v is 1, so this is equal to 1/2. 1, 2, v e minus v e to the power of negative 1 dv. That is equal to, so e is just a number. E is just a constant. So you can just factor out like this. And this is treated like a number. Not treated, this is indeed just a number. So this is 1/2 e minus e to the power of negative 1 v squared, and the v is from 1 to 2. And if you plug in those, you get 3/4 e minus e to the power of negative 1. All right, so that's the answer. Okay, so this is the end of the video. And in the next video, I'm going to work out one more example for this. And then I'll briefly mention what's going on in the case of the triple integral.